Okay, once again. And yeah, like I said, there's 9 tomorrow. It will cover finding critical points. You should know how to find those, what they are. The closed interval method. And which basically means finding absolute max and mins on a closed interval. And also mean value theorem. So included in the mean value theorem is Rolle's theorem. So if I give you a situation that is covered by Rolle's theorem, the mean value theorem will also actually cover that situation. So it's good to know Rolle's theorem, but you can kind of not worry about it for the mean value theorem. Because Rolle's theorem just applies when the average rate of change happens to be 0. So mean value theorem with the average rate of change equal to 0 is Rolle's theorem. So the mean, if you want to study one of the theorems, the mean value one is the more general one. That's the one you're going to want to make sure you know. Yeah. Now, in terms of what we want to move on to, today, again, I mostly want to introduce some ideas. I'm not sure how many actual concrete examples we're going to be doing. And most of the examples for the things I'm going to be talking about, we will actually cover when we do a topic like curve sketching. That's the main way we're going to apply what I'm telling you, although these things are more important in a more general context. And I'll try to allude to some of those contexts, but for the most part, we are going to apply what I'm going to be telling you to figuring out what graphs look like. By extension, you can talk about what the graphs represent. So we're moving on to 3.3. Derivatives and the shape of graphs. So we're going to specifically look at some features that we tend to care about when we're looking at the graph of a function and how derivatives can tell us about when, where, if these features actually do occur. So some important features are to say a function is increasing on some interval. F is increasing on an interval I if f of x1, or let me say f of x2 is greater than or greater than f of x1 whenever x2 is greater than x1 for x values in that interval. Another way to say this is E. F moves up as you go from left to right. Okay. So an increasing function has a behavior where it's going up. As you look from left to right, it keeps going up. Okay? So for any x1 and x2, if I know my x2 is larger than x1, then the y value at x2 will be larger than the y value at x1. So So larger x values will give larger y values. And if a function behaves like that for any two values that you pick in a certain region, we say the function is increasing in that region. It is moving up as you go from left to right. This is saying that as x gets larger, your y will get larger. So another way to think of it. So this behavior is called increasing. Now, it's not difficult to see how the derivative will behave in this context. Considering slope in this context, you'd realize that, okay, if a function is going up as you move from left to right, if you start plotting points and drawing tangent lines, one thing that's going to be clear is that the tangent lines will have positive slope when f is increasing. Right? Start plotting a bunch of tangent lines. The lines will move up as you go from left to right. Applying rise over run to what the slope is, you'll realize that there will always give positive values. And so, therefore, we can now say if f is differentiable, increasing, then f prime will be positive. X on the integral of increase. And of course vice versa. If someone tells you, okay, we have a differentiable function and we know that the derivative is positive, you can assume here that it means that the function is actually increasing. So that's an important interpretation. We've actually seen this sort of before, but I don't think we've ever formally written it down. Right now I just want to formally write it down. Decreasing is a very similar idea. So let's mention that. Let's suppose f is decreasing on an interval I if f of x2 is less than f of x1. X2 is bigger than x1 for x1 and x2 in I, i.e. f moves down as you go from left to right. So you would have the function doing whatever, but it has this sort of behavior. And you realize here, your f of x1 will be larger than your f of x2 whenever your x2 is larger. And so you can say as x increases, y will decrease. So as your x value gets larger and larger, your y values are getting smaller and smaller. And of course, we can talk about the slope here. in terms of being negative. This is going to mean that f prime is negative. Means that f is decreasing. So f prime negative on an interval if and only if f prime is decreasing on the interval. And of course here, we're assuming that the derivative actually exists for us to be able to make this determination. Okay, so that's increasing and decreasing, and in terms of derivatives, it's just looking at the sign of the derivative. If the derivative is negative, that means we're decreasing. If it's positive, it means we're increasing. So we can talk about the behavior of the function. Even if we don't know how to graph the function, knowing about the sign of the derivative can actually tell us about the behavior of the function. So, finding intervals of increase. Right, this is basically where you want to find the regions where your function is actually moving up from left to right and decreasing. As these features themselves tend to be important, and I'll talk about some examples. So I mean, for us, it's probably not very impactful because we're just talking about random functions with random formulas. But generally in the real world, when you're using a function to track something, you're usually tracking something that you care about. You're going to want to know when that thing is getting bigger or smaller in certain contexts, right? So for us, it's just like, yeah, it's moving up from left to right, but this is actually very important. It's very meaningful. It's things you want to know in the real world context. So figuring out when something is moving up as you go from left to right, when it's getting larger and larger over time, versus when it's getting smaller and smaller over time, are very important things to figure out. And if you happen to construct a function to track something, one way to figure out if it's increasing or decreasing is to look at tangent lines, or the derivative, or some approximation thereof. Say other important features. Our local extrema. So normally if you're tracking something that you care about, you'd want to know when does it hit a highest point and a lowest point. Okay? So if your function is tracking, I don't know, you're running a business and your function is tracking your profit, right? You'd want to know when are we making the most amount of money and when we're making the least amount of money and what was going on during those times, right? These are things you'd be interested in. So local extrema, where you hit maximums or minimums, is a very important thing. And we saw in the closed interval case how we could find the absolute max and min, but here we really want to focus on the local ones. And derivatives can tell us about those as well. So, assuming f is continuous in a region, we can find local extrema in that region. by looking at the critical points of f. So let's talk about a local maximum. How do you know when your graph will exhibit this kind of feature? Well, there are two kinds of local maximums we care about in the event that f is actually continuous. We care about things where it can give us like a sharp corner, so our derivative might not exist and we might not be able to get any information from the derivative itself. And there are other times though when the function is smooth, we would call it. And Fermat's theorem will tell us at points like that, the derivative should be 0. So these are, by definition, the critical points. We would want to notice when things like this actually occur. And you'll actually realize that these two things have a certain pattern, right? You will notice that at this point of the local maximum, right, the same thing is going to happen over here. So I can just say ditto. At the point of a local maximum, in the event that your function is continuous, this is what's going to happen. So let's say x naught is the point of, so if we have a local max at x naught, what you can notice about the graph in terms of its derivative specifically is that the derivative to the left is going to be positive, while the derivative to the right is going to be negative, right? You hit a max precisely when you undergo this sort of behavior. You're increasing to a point, but then you stop increasing, that's the biggest you would get. You would necessarily have to decrease from that point to make that point the maximum, right? The maximum means it is the largest y value in the region, which means people can increase up to it, but they can never surpass it. Otherwise, they'd have to decrease from it, and you'll end up with this sort of situation. So you'd end up with a situation where your f prime is 0 or undefined. Right? In this particular case, our f prime would be undefined, whereas over here, your f prime would actually be 0. But in either case, we would identify that point as a critical point, and assuming our function is continuous, we can talk about hitting a maximum. And I would know when a maximum occurs by examining the derivative. If there's a point where the derivative is 0 or undefined, and to the left and right it changes sign in this particular order, on the left it is positive, and on the right it is negative, I can determine that that is a local maximum of the function. This will cover all possible cases. And similarly, I can talk about local minimums in a very similar way. It's again just looking at the signs of the derivative. So a local min, again, we can cover two cases, like a bad case where a derivative is undefined, or like a smooth case. But again, those guys will behave very similarly. Right? At x naught, we'd have the derivative is negative on the left side, the derivative is positive on the right side, and at that specific point, your f prime is 0 or undefined. And this will mean that you have a local min at x naught. Right? And over here, we'd have ditto. This leads us to something called the first derivative test. Here we can identify local maxima and minima by just finding the derivative of a function and examining its behavior. First derivative test. So first derivative test, you want to do this. You first would find the critical points. 2. You would test the sign of the derivative. On each side of the critical points. And 3, we will conclude as follows. So, what I mean by test the sign. So, let's say x naught is your critical point, right? You can pick some random value to the left of it and a random value to the right of it. Right? That doesn't overlap with any other critical point. So we're just assume this is the only critical point stretching for a region. Pick a random number and you actually compute the derivative at those values. So pick the value here, you'd find f prime of that value. Pick a value over here, you'd find f prime of that value. And if you notice that you're increasing over here and you're decreasing over here, and that's a critical point, meaning your derivative is 0 or undefined, then this is a local max. Okay? This means your function is behaving in this manner. On this side it is going up, on that side it is going down, which means at that point you have to have hit a maximum. Similarly, in the opposite case, pick a random number over here, a random number over there. If you realize that your derivative at that point is negative, and your derivative at this point is positive, and this is your critical point, which means that at that point the derivative is 0 or undefined. This means you're going down over here, and you're going up over there, and this gives you a local min. So you tested kind of how you would test inequalities, right? You find the points of interest, and you literally like draw a number line and plug in numbers on either side into the first derivative. That's very important that you're plugging it into the first derivative. So you're not plugging it into the original function, you're plugging it into the first derivative. And this is called the first derivative test. Any questions so far? I think we've been talking about derivatives for a while, so I don't think any of this is too surprising. But that's kind of a process you can go through. Okay, so that talks about increasing, decreasing. Like I said, we'll deal with examples later. I really want to talk about just the features. So we can have the feature of increasing and decreasing, and we can have features of local maximums and minimums. We tend to care about these. There's another feature that we tend to care about, and it is called concavity. Concavity. So I believe this was on quiz 8 bonus. We're actually, in a word, what does the second derivative tell you about? It tells you about concavity. So now I have to talk about the notion of a second derivative. So. here's the weird thing about derivatives, right? Remember how we thought of a derivative? It was the formula that gave us the slope of the tangent line at a certain point, right? And we've also seen that usually when we're taking a derivative of something, it just gives us another function. So we talk about, oh, what's the derivative of x squared? It's 2x. Well, if I look at y equals 2x, that's another function, right? So now, it might stand to reason, sometimes we can probably take the derivative of that other function. So I can say, okay, y equals x squared. What's the derivative? Oh, it's 2x. Think of that as a function, y equals 2x. Could we take the derivative of that? Yeah, derivative would be 2. And that's another function. Could we take the derivative of that? Yeah, it's going to be 0. And then we can take the derivatives forever. So there are times when we can actually keep taking derivatives. So even after we've taken a derivative, we can continue this process and take more, right? Functions for which we can do that are super nice in Calc 2, so next semester. In Calc 2, you're going to talk about those functions. Those are the functions from which you can create power series, and those are super, super cool things. And it tends to be how your calculator will compute things. But let's actually talk about that. So f prime will be other functions. Now sometimes we can take the derivative of f prime. Right? It turns out there are some weird functions that you can only differentiate a finite number of times. Like once you take a derivative, you get something that you can no longer take the derivative of. You're not going to see those very commonly in a calculus sequence, but they do exist. So I have to say, sometimes you can actually keep taking a derivative. So you can have a function which you can take the derivative, and then you end up with something that, hey, I could actually just do that again, right? Now, what does this mean? This is called the second derivative. So basically, the second derivative is the derivative of the derivative. Now, yes, there's a notion of third derivatives, fourth derivatives, fifth derivatives sometimes. These are called higher derivatives. Which I'll probably talk about a little bit more next time. So for the second derivative specifically, let's talk about the notation. There are a couple ways we can define this, or we can write this down. We can use the Newton's prime notation, and we simply put 2 primes instead of just 1. So we can talk about f double prime of x. You can also use the Leibniz notation, and the Leibniz notation. So this is the prime notation for the second derivative. The Leibniz notation would be d squared y dx squared. Now the Leibniz notation looks like that because what you think of is, okay, you'd say dy dx is the first derivative. But what you would do is you would take the derivative with respect to x of dy dx. And then remember how I said the Newton notation, you can kind of think of it as fractions. So I could just multiply the 2 d's, I get d squared. dx is itself, I know there are 2 letters here, but it's thought of as one thing. Let's talk about the change in x. So that's dx squared from those. And then you have that y still just left over. So you end up with this kind of notation. That's the Newton's notation, Leibniz notation. So you can take the derivative of a derivative. And the power just bumps up. I mean, since we're here, let me just talk about the other ones. Sometimes we can continue this process. So I can talk about, for a function f of x, we can have the prime notation, Newton's prime notation. Notation, and I don't know what to call this, the name. So you can have f of x, or you can call it y. This is the original function. Okay. So now you can go and find f prime, which we've been talking about that for a long time, or y prime. This is called the first derivative. You can go a step further, and you can find f double prime, y double prime, this is the second derivative. You can go f triple prime, y triple prime. Oh, I'm doing Leibniz notation, sorry. This will be dy dx. This will be d squared y dx squared. This will be d cubed y dx cubed. This is the third derivative. And you can continue this process. Now, with the prime notation, eventually you can imagine that if you continue this process, by the time you get to like the fifth derivative, writing all these notches, it kind of gets silly at some point. You don't want people to have to be reading your work and they have to be like literally counting when they're reading something. So eventually, if they have too many primes, you change the notation a little bit and write it more like an exponent. But the difference between a regular exponent and the derivative this is the prime, Leibniz name. So eventually, it comes down to the point where it can get kind of silly. So let's say we're at the 10th derivative, right? The prime notation would have the following. You would put the number 10 and you'd put it in parentheses. Whereas this guy's going to be d10y dx to the 10th. This is the 10th derivative. And dot, 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 dot. You can generalize this to talk about the nth derivative. We take a derivative nth time, where nth is just some positive integer, or non-negative integer, talk about that. And the notation becomes like that, versus this. That's called the nth derivative. So you can generalize the notation in that way. So that being said, so if you look at something like this, that means y squared. You see this, that means the second derivative. Right? So parentheses in the power, it means something. It means something very important. And sometimes, just to be cheeky, you might think of the original function as the 0th derivative. This is the guy that we get from not doing any derivative. It's the original function. We can think of it as the 0th derivative. So we can talk about this theory where we develop higher derivatives. And functions that have the property that you can just keep taking derivatives forever, They're super nice functions, and we can often use them to approximate some not nice functions. And to do that, we would develop something called a power series, but that's Calc 2. But you can have the notion that, okay, when I take the derivative, I can think of this as getting another function, and ever so often, I can actually just keep doing this. Right? So you can even think of if your y was e to the x, I can take derivatives of that forever. I just keep getting itself back. Right? The first, the second, the third, the fourth, the fifth, all those derivatives, they're all e to the x. I can do that forever. Right? You can think about sine. I can take those derivatives forever. Derivative of sine is cosine, derivative of cosine is minus sine, derivative of minus sine is minus cosine, derivative of minus cosine is positive sine, and you just keep going, right? So we can keep taking derivatives. The one I want to really talk about now is the second derivative, though. How does the second derivative help us? Let's actually start with a definition. F of x is called concave up in a region if its tangent lines are always below the function in that region. Right? So I've just defined for you what it means for a function to be quote-unquote concave up. This is the property such that at any point in that region, could look like that, it could look like this as well. So this, for example, this or that will have this property. You will notice something with these functions. If I were to plot points on this curve and sketch a tangent line, at any point, you'll notice that the tangent line is always going to be underneath the function. It's not going to cut the function and go above it. The tangent line is always going to be below the function. I can do the same thing here. Plot a tangent line at a bunch of points in this region. You'll notice that if I were to sketch the linear approximation, my tangent lines will always be below the function. You might be like, okay, so what? Question. How would you describe what's happening to the slopes of the tangent lines? So if you were to compare this slope to that one, compared to that one, compared to that one, compared to that one, how do you describe it? Let's say for argument's sake, I told you, okay, the slope here is minus 10. What would you say this one is? Or what would you say this one is?
0 greater.
Closer to 0, right? What about somewhere in the middle?
-5.
Minus 5, right? We're just throwing out random guesses here, right? What you'll notice is it starts out very negative, less negative, 0. You'd realize that if you were to kind of continue this pattern, you would almost expect it to start becoming even positive, right? If you wanted to continue this pattern. You can imagine like this is going into that. Versus here, this one is slightly negative. At some point, it'll be 0, but now you notice over here, it's getting more positive. One thing you can notice about the tangent line of a function that behaves like this is the slopes will be increasing. They're getting larger and larger as you move from left to right. Now, how can you talk about the slope increasing? Well, we know what it means for a function to increase. We just spoke about it earlier. A function is increasing if its derivative is positive. But now if we're talking about the slopes, what function would describe the slope? Well, the derivative would describe the slope. Right? But slope increasing would mean that the derivative of the slope is positive, i.e. the derivative of f prime, which is the slope, is positive, i.e. the second derivative is positive. Whenever a function has this sort of behavior, we can conclude that if it's, assuming the existence, right? Every time I talk about a function, we're assuming it actually exists, right? If I actually can take a derivative, I can't make this conclusion. But assuming that I could take the second derivative, it would necessarily mean that it has to be positive whenever the function has this sort of behavior. Because that sort of behavior will always result in an increasing slope. If you look at the function itself, the y curve, it's increasing. Here the function is decreasing. Whether or not the function is increasing or decreasing, looking at the slopes, they are increasing in both situations. So here, you'll notice that f is increasing, and f prime is increasing. Here, you have that f is decreasing, but you still have the fact that f prime is increasing. So that is the common thread here. The function itself is changing the behavior, but the derivative isn't. Once the derivative maintains a positive sign, whether or not your function itself is behaving however it wants, we cannot also say that the function is, the slope of f prime is going to be positive. In other words, we can say the following, and we're pretty much out of time, so I'll have to define concave down next time, but it's pretty much going to be the opposite situation of this. So we can say the following, i.e. f is concave up in a region whenever f double prime is positive in that region. This gives a shape, and by the way, shape is the main thing here, like this. Right, so you can have it looking like this, it can be decreasing, or it can be increasing. And so this leads to a mnemonic. Concave up, like a cup. Okay? So your function is concave up. You're thinking of its shape like a cup, something you can hold water in. Concave up like a cup, you're smiling, you're happy, you're feeling positive, the derivative. The second derivative is positive. Concave up like a cup. Concave down is going to be similar. Concave down like a frown. right? It's going to be when you bend this way, you notice that the tangent lines are always above, and the secondary will always be negative. So you don't like a frown, you're negative, you're feeling sad, right? The secondary tells you about shape. And the shape we can describe in terms of a word called concavity. And basically concave up means you're shaped like a smiley face, concave down means you're shaped like a frowny face. That's basically what we can say. And the secondary can tell us this based on its sign. So we'll talk a little bit more about that tomorrow.